And I'll be presenting on topic 2. So topic 2 involves assessing the seasonal variability of swimmers with the ultimate goal of creating an individual and aggregate benchmark tool. So this would be used as a feedback tool to both coaches and athletes. And through a number of case studies, it was found that the periodic monitoring is effective in assessing swimmers' performance as well. So moving briefly onto methods, there were 111 observations of 25 different swimmers, and the categorical variables recorded include gender, season stage, and stroke as well. The continuous variables were peak velocity, critical velocity, drop-off percentage, and also area under the curve. It's also important to note that all of the 25 swimmers did one stroke each, just for consistency and ease of data. In terms of methods used, Tukey's 5-number summary, standard deviation, mean, and side-by-side box plots were considered. Linear regression was initially used, but due to inflated R-square values, a mixed effects model was used to adjust for this. Furthermore, Tukey's significance test and regression trees were also used to look into this data a little bit further. So moving straight on to regression trees, it was found that breaststroke is the most significant predictor of area under the curve for these swimmers. The next partition was by gender, so male or female there. And then it was found that with the male partition, potentially because there were less observations, there was no further partitioning. And this resulted in males showing a higher mean squared error than females. And overall, there were 81 observations from females and only 30 from males. All of this was corroborated by Tukey's on a significance test as well. So moving on to a box plot of the seasonal variations in non-breaststroke peak velocity. So that is backstrokers and freestylers. So from this, it was found that there was increased median peak velocity over the course of the season, which actually coincided with a drop from early to mid-season in terms of critical velocity, and then an increase in critical velocity late in the season as well, basically implying that their endurance improved over the course of the season. So this plot in particular, and this particular subgroup, could start to form the basis of this benchmark. Moving on to the mixed effects model that was fitted for peak velocity amongst these swimmers. So it was found that breaststroke had over twice the influence of freestyle, that is using backstroke as the basis. The standard error of the intercept was acceptable. However, the standard error for season differences as well as freestyle did limit the explanatory power as well as some of the validity of the results as well. So that was just a minor challenge in terms of that particular model. And moving on to the discussion, here I've got a table of the observations by each subgroup. So the blue denotes males, red denotes females. And as you can see, there was some challenges in terms of observations from these particular subgroups. So those with less than 5, it was particularly challenging. And indeed, for male freestylers, there were no observations in the early or late season, which made it a little bit of a challenge in terms of forming that benchmark. And indeed, there were also no male athletes that had observations for early, mid, and late season. So that's why they were subsetted with the box plots by female, just to get more meaning and to sort of start forming that benchmark as well. So it's expected that we'd be requiring probably at least 10 observations for each of these subgroups in order to make a really effective benchmark. And it may also be useful to consider some of the outcome metrics and also distance specifications as well. So for example, if we see that an athlete does particularly well at a particular meet, then we may either use that as their individualised training method and those metrics, which may also lead to a sort of aggregate model being established as well. So in conclusion, the main outcomes that were found is that the non-breaststrokers' peak velocity increase, as mentioned before. And there's also lots of room for further methods and investigation. So Bayesian regression and multi-level models are certainly something that could be considered for this data set. I myself don't yet have those skills and only had a few days to work on this, but I'd really love to look further into those possibilities. As well as that, it would be very interesting to look into individual variability across multiple seasons, not just within season. I think that this could lead to really interesting long-term effects in terms of benchmarking for new athletes as well. There's potential for the area under the curve calculation method to be slightly improved, and hopefully with further investigation, it may lead to the construction of a really effective and insightful benchmark tool, both for the individual and the group as well. So happy to take any questions regarding the report or any of the technicalities.
It was kind of my data set, so I'll
yep.
That's awesome, Michael. Thank you for that. That's super. There's a lot of information there that's really helpful for me. So even things just like we need at least 10 observations for each of that sort of stuff.
Yep.
We don't have enough observations about males to make that sort of those inferences. Yeah, that's really useful information for us to have. So
sure.
Thanks for your work. It's really interesting, some of the outcomes that you've got. So
thanks. Yeah. Thank you. Yes, Kerry.
Nice job. Nice talk.
Thank you.
Can you go back to your decision tree?
Yes.
And can you just walk people through that? Are you able to talk through that? How you actually like so the software or the analysis picks out which variables are important.
Yes.
And then it does the splits, isn't it? So it's actually taking splitting up the data into subgroups by which variables are important, and then comes up with sort of subgroups at the bottom that are common. So can you just walk people through how you actually see that? Because it's different from a regression.
Sure.
Isn't it?
Sure. Yeah, so with the regression tree, as Kerry mentioned, it goes in order per petition in terms of which is the most explanatory predictor. So it was found that breaststroke, in terms of area under the curve, made the biggest difference among those groups. And then if we just look at, for example, on the male side, on the non-breaststroke side, which is on the right, we found that the next most important variable amongst that group in terms of explanatory power was gender. So as I did mention, because there were fewer observations from males, there was no further petitioning. As we can see there's 13 observations from males at that point.
Then if it says gender equals female there,
Yes.
that's true, you go to the left.
Yes, that's
And
right.
if it's false, you go to the right.
Yes.
So at the top, for example, stroke is equal to breaststroke. So if it's not breaststroke, you go to the right.
Yes.
And then if you're not a female, you go to the right again, and then you end up just straight down into the bucket.
Yes. Yeah.
If you are a female, then you keep going.
Yes, exactly, yeah.
Keep going.
Yeah. And then further from that, it was found that the next most important thing among female non-breaststrokers was whether it was early season or not. So as we can see, when it was early season, basically their area under the curve was lower. But if it wasn't early season, i.e. mid or late season, then the next most important petition from there was whether they did backstroke or not. And then from there we can see that that backstrokers had a slightly lower area under the curve than freestylers, which basically just explains that freestylers were faster. And I'd like to mention as well that we would have probably seen similar results in terms of the petitioning for males had there been a few more observations, because overall both males and females did show similar trends across the strokes. So it would be expected that those mean squared areas would be reduced there as well. Yeah. Yes.
So I don't have any familiarity with this technique at all, but I think it's really interesting. So I just have sort of a couple of questions around it.
Sure.
It seems to me that you would need a fairly large number of observations to be able to build it. Is that the case?
Yeah. So I think that 111 is still, in terms of the accuracy that we wanted, because you can take it to such a level that you make even more subgroups from there, but I suppose it does get to the point where it sort of becomes meaningless because it's just telling you, oh yeah, males who do freestyle in the early season, which is sort of already things that we know, in terms of if you subset it too far. So I suppose that with that, in general, it may be more useful to have those more observations. You're absolutely right. And I'd expect a similar thing for males, as has resulted there for females as well. Yeah.
You can still build these with a smaller number of observations,
Yeah.
but you just don't get as deep a tree.
Right.
So then you just get
Or as
shorter
wide
categories.
a tree,
Yeah,
as
that's
deep
right,
or as
exactly.
wide.
So
Yeah.
Exactly, yeah.
Your subgroups will have more variation.
Yeah. But it wouldn't really be valuable if you had like n equals 10. You can't do a whole lot with that.
You can't do a whole
Not
lot
in, yeah.
of regression either,
Right.
so
Right. Yeah. Exactly. So.
Parametric regression is better for some examples
Yeah.
compared to non-parametric regression.
And my second question is just,
Yep.
those are very discrete sort of categories. I'm wondering, can you take more of a continuous data sequence like body weight and just make a cutoff in there like above or below 80 kilos and then split that? And would you be able to, would this method be able to sort of automatically identify where would that best cutoff be?
Yeah, so you can certainly create cutoffs in terms of different continuous variables. I don't think that a regression tree itself can determine how you should subset and categorize those particular ranges. It can?
Yeah,
Okay.
I think because you've had the categorical variables or the
Okay.
variables already, haven't seen that?
Right.
Yes, exactly. So putting the continuous variables and we'll work out where the split should be.
Ah. Great.
Thank you.
Just.
On that one, would you need a categorical variable as well then? So you have, how would that work, the split then? What would that look
creates
for?
a categorical variable.
Yeah, but what's the outcome was it looking for?
Oh, so down the bottom you,
Yeah.
you either can have a continuous variable or you can have a categorical variable.
So if you had a continuous at the bottom,
Yeah.
what would it look for in terms, would it look for the biggest significant difference between
Yeah,
those two groups?
that's exactly right.
Okay.
So it's looking for most smallest variation within the groups and biggest variation within the groups. That's what it's on. And if it's a categorical variable, it looks to have most similar